Hey guys, welcome back to class. Today we're going to continue our discussion about the ideal gas law. One of the interesting things about the ideal gas law is it wasn't discovered or it wasn't created as a whole. It was actually discovered in pieces, right? The whole law is this: pressure times volume is equal to the number of moles times some constant multiplied by the temperature. Um, the first one we're going to talk about is Boyle. Boyle discovered the relationship between pressure and volume. Let me get my picture out of here. The next one we're going to talk about after today is Gay-Lussac. He discovered the relationship between pressure and temperature. And then the next one we're going to talk about after Gay-Lussac is going to be Charles. Charles discovered the relationship between volume and temperature. And then finally, I want to talk about one more scientist who contributed to this, and he discovered the relationship between volume and number of moles. And then you could have gone on to pressure and number of moles, but at this point, the scientists started realizing that they're actually all working on the same equation, even though they think they're working on separate things. So the first one is Boyle, and the equation Boyle discovered was this one. You have, is this too small? Yeah, it's too small. You have a certain pressure, and you multiply that by a certain volume, right? Let's call that the initial pressure and the initial volume, pressure 1 and volume 1. And then you change the pressure and volume of that gas, right? You change it. You change the pressure, and what that does is it changes the volume. Well, if you multiply this pressure times this volume, you're going to get a certain constant, a certain number. And if you multiply this pressure by this volume, the new pressure by the new volume, you'll get that exact same number. And that was his discovery, is that you can get the initial pressure and the initial volume and multiply those together, and you'll end up getting the exact same number as if you multiplied the second pressure and the second volume together. So this was his starting equation that he discovered. And if you were to graph that equation, it would look like this. You would put pressure on this side, pressure, I can't spell it all out, pressure, and pressure is typically either in ATM or pascals. I'm going to just write in ATM for now. And volume. Now, as a typical X, and this is just a graph, typical X and Y axis, as you go up, it's increasing, and as you go to the right, it's increasing. So this dot, between this dot and this dot, the second dot has more volume, right? But they're at the same pressure. Between this dot and this dot, the higher dot has a higher pressure, right? Now, what he realized is when he graphed the pressures and the volumes, is that they followed this trend. As you increased your pressure, as you increased your volume, as you move to the right, you're increasing your volume, your pressure actually drops. And the inverse is true as well. As you increase your pressure, right, you go this way, you're increasing pressure, but your volume begins to drop. So he discovered that these were inversely proportional. They were oppositely related. Another way to think about that is if I have 3 times 4, that equals 12. In order for those two numbers to equal the same, to still equal 12, let's say I raise this 3 to a 6, right? I raised that number. Now I need to reduce this 4 to a 2. As 1 goes up, as the 6 goes up, as the 3 goes up to a 6, the 4 has to go down to a 2 in order to maintain the same product. So that's what this relationship is really saying. As 1 goes up, the other goes down because they equal this same constant. All right, and so let's move on to an example problem. Like what can I really ask you knowing this stuff? Well, I can give you a sentence like this. A gas has an initial pressure of 100 kilopascals. There's a decimal here. That means that I have 3 sig figs. 1, 2, 3. Don't forget that. Initial pressure, well, that's the 1, right? 1 comes first. So your initial pressure is 100 kilopascals. kPa. Don't forget the dot there. That shows I have 3 sig figs. The volume is decreased from 12 to 7.5 cubic centimeters. So it starts at 12 and it goes down to 7.5. So my initial volume is 12. And the test question is going to be very similar to this question. So make sure you understand exactly this question. And it goes from 12 to 7.5. 7.5. Let me fix that 5 right there. .5 centimeters cubed. And it says, what is the final pressure? Good. I read this correctly because that's the one I don't know yet. Here's our equation, our starting equation, right? And we want to make a working equation, an equation that we can actually use to solve for final pressure, because what we have now, you can't actually solve for final pressure. So we have P1 times V1 equals P2 times V2, and we want P2 by itself. In order to get P2 by itself, you divide both sides. That's too big. You divide both sides by V2. And what that does is it cancels V2 on this side, and it puts V2 over here. And we're left with just that one step got us P2 by itself. So we know that P1 times V1 divided by V2 equals P2. And that's our working equation, right? It took one step to get there. Now we're going to plug those in. P1, well, P1's up here. That's 100 kilopascals, which is kPa, times V1, which is 12.0 cubic centimeters. And that's going to be divided by V2, which is 7.5 cubic centimeters. And then my answer is going to be P2, which is what I'm looking for. Now, something to keep in mind, two things to keep in mind. You want to keep track of your units. Centimeters cubed, that's squared. Centimeters cubed divided by, this one's also squared. Cubed divided by centimeters cubed, it cancels and you're left with kilopascals. So my answer should have units of kilopascals, which checks out because I'm solving for pressure. 100 times 12 divided by 7.5. Let's turn that on, put it in our calculator. 100 divided by, times 12 divided by 7.5. You get 160 in your calculator. Now we want to make sure we have the right number of significant figures. My answer right here, right now, is 2 sig figs. In my calculations, I use 3 sig figs, 3 sig figs, and 2 sig figs. So because my lowest number of sig figs is 2, I do want 2 sig figs in my final answer. And look at you, I already have that. Step 4, I put here just so you can either do it together like I did up there, or you could do it separately. We know we had our kilopascals, kPa. We can just drop the numbers and use the units. And we had centimeters cubed. And then we divided it all by centimeters cubed. Right? Centimeters cubed cancels centimeters cubed, and you're left with kPa on top of the denominator, and that was the unit that we got. So we double checked our units. That's something you always want to do. And that's it. Bye guys. Have a great day.